Hello everyone. I'm very happy to participate in this sharing about the use of Iceberg. The theme of this sharing is uniting petabytes of solid data with Apache Iceberg at Tencent Games. First of all, I will introduce myself. My name is Chang Hongli. I work for Tencent and as a backend development engineer, working in the field of container and big data. Currently responsible for the development and optimization of StarRocks FE components and Icebergs. Next, I will introduce my team. Tencent Games Public Data Platform Department provides basic data platform to support 400 of Tencent games, using data to help game commercialize and improve game qualities. Our lakehouse product has been already running online and has the following features. The first is support writing trailing of record ID, and the second is second level data fairness on mutable data, and the second is the data in the Iceberg has reached PB levels. Now let's start my sharing. This sharing mainly includes 4 parts. The part 1 is background. I will introduce the previous architecture and the problem we face, and why we use Iceberg to build our lakehouse product. Part 2 is the technological architecture overview, our new lakehouse architecture and some of its features. And part 3 is the enhancements that we added to address the challenges. And the last part is the summary. This is our original architecture. As can be seen from the picture, game's logs were stored in Hadoop file system, while application layer data was dispersed across traditional databases like MySQL and PostgreSQL. Moreover, real-time data is stored in Dude. It is not only the costs and challenges of managing these disparate data sources. This storage schema made data usage difficult and often created bottlenecks in accessing critical information. The old system used a lambda setup, which means one system for real-time data and another for offline data. Manage 2 data paths. Data separation paths is complex and costly to maintain. For the query, all data just be pre-processed, include pre-aggregation and denormalization in Hive before moving to Postgre for reporting and dashboard. This long process is not only complex and a waste of computing and storage resource, but it also locks the data into a single view format. Any schema change needs reconfiguring data pipeline and data backfilling. Faced with these challenges, the growth of trillion of data every day, the gap between scale of data and class capacity widens. A new system is greatly needed. New system should meet this need. Subsequent query latents able to quickly execute query requests. And the second point is storage and recognize petabytes of data. And the third point is low optional overhead and simple operation and maintenance. After research and comparison, we found that Iceberg can meet our needs. Iceberg is an open table format for analytics dataset, set up from Hive, and support schema evolution, hidden partition, time travel, vision rollback, and this feature can enable data warehouse workload on open standardized format and uni workload on a single source. The easy data governance simple architectures. In order to ask second levels query and data fairness, we use StarRocks as a query engine. StarRocks is a generation blazing fast, massive parallel processing query engines. There are many features that meet our needs. For example, the first is support vectorization engines, and the second is higher concurrency, and the third is enable real-time analytics on community data. And the fourth is a simple architecture, consists of only two types of process. FE is the manager node, storage metadata, manager client collection, and query plan. And B is a storage and computer node, responsible for query execution. So we build our lakehouse product based on Iceberg and StarRocks, and has the following features: a simple and scalable architecture, only consists of FE, BE, CN, and Iceberg. And the second is a second-level query latency, ability to query with seconds. And the third is second-level data fairness on mutable data. This is our cloud-native lakehouse architecture based on StarRocks and Iceberg. Realize vectorized engines, hot and cool data separation, resource electric scaling, providing a balanced solution of high performance and low cost for the gaming industry, as can be seen from the architecture diagram. Through StarRocks, Iceberg, unify offline and real-time data import and data queries. All data is stored in Iceberg, and the scene is used to achieve electrical and resource isolation. Hot data is stored in BE to maintain data fairness. C is a set of scene group is a set of scenes with the same label. I will introduce it later. Next, I will introduce second level data fairness with mutable data on Iceberg data writing process. Real-time data is ingested into StarRocks through consumer MQ, and that sync task will be generated in FE. Then the task generated it will execute the execution plan scheduler. Tasks will be delivered into BE and write into ORC format file to remote storage. After ORC writed, these files will commit to Iceberg. After this step, the data import and update are completed and entered into the lake. Hot data in data warehouse will be deleted. From the picture, we can see the hot data partition October 3rd, 2nd will be expired. It's not only ensure a second level fairness of data, but also realize single source of true data on Iceberg. For query, utilizing StarRocks table as the point of access for hot data in StarRocks and query data from both StarRocks and Iceberg, as shown in the figure. When querying the data from 2nd to 6th, the query predict will split into scan node. For example, OLAP scan node will read data from October 3rd and October 6th. Iceberg scan node will read October 2nd to October 3rd. After Lakehouse has been running in production for a period of time, with the success of business and the amount of data continue to increase, we also encounter many challenges. The first is a large number of query requests during peak period require a large amount of computer resource, but at a low time, computing resource cannot be dynamically destroyed. This causes a huge waste of resource. And the second is a circle query for a large amount of data in Iceberg, consume a large amount of CPU and memory resource. This causes other requests or data field import failed and or slowed down. A resource isolation function is poor. And the second is with the continuous import of data. A large number of data files are generated in Iceberg. And Iceberg gets execution plan by plan task interface slower and slower. In response to above problems, we have made some functional optimizations. The first is electric scaling of computing resource. Computing resource requirements are different at a different time of the day. We developed a Celos CN node storage period computing node. Utilizing the feature of Kubernetes, CN runs as a container in Kubernetes. It is easy to deploy and maintenance. From the picture, we can see that a user sends a create the CN request to Kubernetes, and StarRocks operators will create CN and register to FE. After this step, CN deployment completely. the next features is support electric scaling. Auto scaling is very friendly to a large numbers of data files in Iceberg. And the more important feature is that it can exchange data with BE to speed up the query of hot and cold data. And the second feature is resource isolation. With the help of Kubernetes, we can quickly create a scene of a group of scenes with the same label. We call it scene group. For one scene groups, it have a different specification. For example, and it have a 4 core and 8 memory configurations, and the other is customer numbers of scenes with each scene groups. And after a task finished, it can destroy scene group. As can be seen from the picture, we can see that one task can use a special scene group. Even for Iceberg compact task, it also can use special scene group. The third optimization point is to solve the problem that Iceberg meta files need to be read remotely over time. So we RIU fill our cache in customer's HIF catalog to cache immutable meta files, include metadata files, manifest lists, and manifest files. Because these meta files are immutable, so the cache process is simplified, owing to localize and configure time to live when reading for the first time. And the first optimization point is to solve the problem of slow Iceberg execution plan. By analyzing the code flow of Iceberg plan task interface, we can see that during each query, after trimming the manifest list, we got some manifest files, which contain a large number of data files. In this step, querying and filtering qualified data files take up a lot of core resource and is a time-consuming operations. So the column static of data files are pre-calculated and cached in StarRocks tables. As can be seen from the pictures, a period task will read many manifest files one by one to calculate data file statics, include manifest path, column name, data file path, and data file size, record count, mini or max value, and save them to StarRocks tables. For query from the Iceberg, the execution agent will auto rewrite the predict of query and filter out the data files that meet the condition from the data files static tables. After got the data files, continue to query the real data. For example, query table with predict event ID larger than 4 and event time larger than 30 days. We will change the circle to query the data file from StarRocks tables, and the circle will change to column name equal to event ID and max larger than 4. To join itself on column name is event time and mini max value is equal to 3rd. Then got the data files. The optimization of the Iceberg meta file has brought good benefits. The execution time of the plan has been reduced from 65 seconds to 6 seconds. Electricity has also saved tens of thousands core resources. In addition to this, we also made some other optional configuration on Iceberg. First is clean up the snapshot to reduce the size of metadata files. As we know, data is continuous writing to Iceberg. A lot of snapshots is recorded in the metadata files. We'll call the writing and reading too slow. The second is data file compact. To reduce small files and speed up queries, because we consume messages from the MQ and writing them to Iceberg, and this data is in MQ is real-time data. To make sure the data fastness, this import will generate a large number of ORC files, and each ORC file is small. Even increase the commit to Iceberg interview time does not solve these problems, so we add a compact task, use scene group to merge files. The third point is to recognize data files according to partitions to reduce redundant data file pairing. Since offline and real-time import run together, the data files contained in many fast files involve multi-partitions. This problem will cause redundant reading and pairing when querying. This above is my sharing in this time. Thank you.
Hello, thank you, Hongli. So I will be reading out some questions and answers that came up during the talk. If you do have any further questions or follow-up questions, you can type them in the Q&A tab to the right, and we will translate your question. So that might take a couple of minutes before they are answered. But let's look at the Q&A that's come through so far. So one of the questions we have here is, what is the technology for sub-second response time for complex queries? And Hongli has answered here, use StarRocks as a warehouse and as a cache for the lake, caching hot data. For lake queries, use elastic computing resources. So thank you, Hongli. Then the next question we have here is, what workloads are you putting onto StarRocks versus Spark versus Trino, and why? Any performance comparison to share between StarRocks, Spark, and Trino? Hongli has answered, because a warehouse is needed for cache, there is no comparison with Spark. Comparing StarRocks and Trino Lake, in our scenario, there is a 10 times improvement. That's quite impressive. Then also he added new flexible computer node CN, which is more flexible than Trino. We have another question here. Are you using VLOX open source for C++? I hope I said that right. SIMD vectorized engine. And Hongli has answered, we realized it ourselves. Let's see if there's any more that have come through here. No, I think that one is just all of them. There is another one here, our statistics per partition. Let's see if we can get an answer for that one from Hongli in the time that we have. Did I answer that one? Oh, there's another one here. Pre-calculated cached data are put in your own set of metadata, question mark. Hongli has written, put the statistical information of data files into a table in a warehouse. I think that's everything that I've answered so far. I'll just wait to see if there's any more answers that come through. But Hongli, that was a really interesting presentation, so thank you. Oh, we've got another question come through as well, Hongli. Did you have trouble keeping, they're all jumping around now, keeping the column statistics materialization stay up to date for optimizing query planning? And another one, what's the maintenance cost comparing Trino and Rockstar? So if you could translate and answer those, that would be amazing. Just to say, though, while we're waiting for those responses, there will be an evaluation form that pops up. If you could just answer it, it's just one question. It'll just help us improve for the next Iceberg Summit. Just waiting for some more to come through. Don't forget that we have all of our sponsors in their booth, so do check out their booths while you're on the event. We've got some great sponsors for this event. Let's see. We've got a question here. So our statistics per partition, and the answer is from Hongli, each data file. There we go. Fantastic. Great. Just waiting for any more answers to come through. Just a comment from Daniel saying impressive architecture. Thanks for sharing. So some good feedback there, Hongli. We should have some background music. I should have had some ready for while we were waiting. I won't sing. Everyone will just drop immediately if I did that. I'm just waiting for any other answers to come through, Hongli, from the two that are remaining. We've got one here. So the question was, did you have trouble keeping the column statistics materialization stay up to date for optimizing query planning? And Hongli has answered, it went relatively smoothly. Real-time data still needs to be calculated. Thank you, Hongli, for answering that question. I think there's just one last question left that hasn't been answered yet. What the maintenance cost? What is the maintenance cost comparing Trino and StarRocks? So we'll just get that translated for Hongli and he can answer that one for us as well. Great. Fantastic. Just quick translation. Very quick. It's impressive. Thank you so much. And someone's written here, shout out to Hongli for sharing. This is just a comment, not a question, Hongli. Shout out to Hongli for sharing, especially for doing it in English, so I was able to understand. But also considering the time differences, he really appreciates it. So that's from Tobias. So well done, Hongli, and thank you. I agree. Very impressive. Very impressive indeed. So we're just waiting for that final answer to come through. So while we're waiting, don't forget to complete the evaluation question for this session. That should have popped up in the corner. If you're watching it live, the next sessions are starting soon. But in the meantime, don't forget to visit the sponsor booths in the expo area. I think everyone's hanging on, waiting for that final answer. Must be a popular question. Oh, we've got one here. What's the maintenance cost comparing Trino and StarRock? Did I just read this? I'm going to reread it if I didn't. StarRocks has only two components. The elastic nodes are deployed on Kubernetes, and maintenance is also very difficult. And then we have another answer here. So the question is, are most of the features mentioned here available to open source StarRock or just internal available in Tencent? Hongli has answered, the functions we developed have also been submitted to the community, such as Elastic Node CN. He's added the feature of data syncing into the lake is still being submitted. There we go. I think that is all. There's another one here. I can't remember what I've read and what I haven't, so I'm just going to read this one out as well. Did you have trouble keeping the column statistics materialization state up to date for optimizing query planning? Oh, I have read this. It went relatively smoothly is the answer. Real-time data still needs to be calculated. So I think that's all the questions now. So thank you so much, Hongli, and Sean as well from Tableau for translating. It's really appreciated. Thank you so much. That's the end of the session. Goodbye.